Thank you very much, Luke. Thanks for the kind words, and I'm very excited to be here in that beautiful building in front of all of you. I wanted to share some experience and insights maybe on where AI and computer vision are today, and where I think they're going to go next, and where the big opportunities are. Obviously, you have an idea of what I'm going to talk about in terms of application of computer vision and where the next big thing is. And I had the chance to spend some time with your machine learning computer vision team this morning, which do amazing job. So let's, without further ado, let's jump right into it. So Luke presented my background a little bit. So just wanted to highlight the fact that even though I've been managing my companies for a long time, what I like to do deep down is what's on the right side, is reading papers and coding. So actually doing academic paper reading and implementing, right? And deep down, I'm an engineer. I have to do some management because I have to hire people to help me do things. It's kind of a necessary evil, but what I really like to do is implementing and making things work. I also spend a lot of time with startups and VCs and accelerators because I've been doing that for a long time. And there's always a little bit of my time where I don't know where it goes, but everybody's like that, right? So, and I'm French, nobody's perfect. All right. So among you guys, how many of you are familiar with deep learning? I've heard the term. All right. How many use it or have ever used it practically? Okay. How many of you use it on a daily basis? All right. Okay. Same. So, okay. Just for me to know, what I need to, how deep I'm going to go into the details. But let's start with a little, a step back about what deep learning is. Right? You've probably heard that keyword in the last, 3-4 years. Basically, since 2012. It became one of the hot buzzwords in the machine learning and computer vision community, right? Deep learning is a pretty big change compared to traditional computer vision approaches. When you want to do traditional computer vision, you build a model, right? You want to analyze, you want to detect a road, for example. You're going to decide that road has a white marking in the middle, and it's rather dark, and there's maybe some green on the side. So you're going to build an explicit model of that. You're going to be looking for things that are green outside of things that are black, and with little white things in the middle. You're going to be building models like that to understand what's in images, right? That's what's called explicit models or designing features, right? Deep learning is very different. It's an end-to-end system. So you plug a system that looks like a brain on the pixels of an image or a video, and the output of that system is some classification, for example, right? Saying what's in the image. But it's an end-to-end system. There's nothing explicit about it. All you know is that that system kind of looks like a brain, right? It's made of neurons connected to each other. They contribute to, so one neuron connected to another. They connect to it, add to a sort of cost function. When the cost goes above the threshold, you trigger something, and that's how it works. It's a big set of linear combinations, basically. And it's very big. So it started working back in 2012, basically, when we had enough compute power to build networks that are big enough. In traditional data analysis, you think that to have a model that works, you need a lot more data than the parameters of your model, right? So you want to build a regression model to approximate a phenomenon with a plot, a line, for example. You will need significantly more samples than the parameters of your model. Well, in deep learning, you have a lot more parameters than what you learn it on, actually. You could have a lot more, which is kind of not natural, but it still works. So back in 2012, neural networks started beating traditional models in standard tasks like understanding what's inside an image, like saying that this is a lion. That's when neural nets started beating traditional approaches. So Deep learning since then has brought a lot of things to a lot of domains in vision, right? And other domains too, but I'm going to focus on vision specifically today. So scene classification, object detection, you can see some examples. You probably all saw demos like that, and you probably all saw that Google understands what's inside your photos now and things like that, right? So understanding that it's a dog, a person, understanding the boundaries or even the segmentation, like the exact borders of these different objects. That's what deep learning can do in vision. Deep learning has also beaten the human accuracy in some tasks, right? So for face recognition, for example, Deepface by Facebook performs at 99.8% accuracy on a standard data set. The human accuracy on that same data set is 99.7, right? So deep learning is so good that it becomes better than humans in some cases. So that's for face recognition. So it's not all deep learning technically. Some parts are not deep learning, but it's mostly that. Pose estimation, you see in the bottom, these little dancers can automatically be detected. We can understand what they're doing, track their motion, understand their pause. Action recognition, so I focused on security cameras. We want to detect if somebody is stealing something from a shelf, trying to enter, to break into your house. This also works really well. And I mean, I could go on and on, right? There's lots of examples of use cases and features that were completely disrupted by deep learning and these deep neural networks. It's very easy to recognize when an algorithm is implemented by deep learning because it just works. When it's explicit, designer features, things tend to work but always have little issues. You can get to accuracy around 85, 90%, and then you can see that in some cases that were not understood by the person who designed the algorithm, it's not going to work at all. When it's deep learning, because you're learning the features, you're learning the essential parameters of your system, it works a lot better, a lot better. So it's always easy to recognize when it's a deep learning algorithm or not, because it just works better, it generalizes better. So following that, so these were more like core technology features. There's been a lot of applications that developed around this progress in image understanding and computer vision, right? Advertising, so targeting advertising based on the photos you look at. Online brand monitoring, seeing what people do with your products online. If you're a handbag maker, for example, you can see in which environment and what people do with your products. Trend spotting, seeing overall, based on what people post on Instagram, what is trendy or not, with what kind of population, all that based on image analysis. Remote sensing has had a new sort of rebirth, right, of the industry. Remote sensing is one of the very old domains of applications of computer vision. For a long time, it was boring, old school application that was only military. And today, there's a lot more satellites in the air, and there's a lot more things you can do with images. So there's a lot of startups that are popping up on the market doing remote sensing. Medical imaging is also undergoing radical transformation right now because of the accuracy and the quality of the analysis you can get now. There's a startup so that was completely impossible to imagine like 5 years ago. Startups in medical imaging were really rare, but now it works so well that you can do it again. So there's a startup that started recently that put up a website where you can upload your own X-rays or your own CT scans, and they'll give you an idea of what's going on. It's all weird, but it works actually. It works pretty well. So medical imaging is also being completely reinvented today. So photo tagging on your home photo account, access control with biometrics, security cameras, which is what I do in and out, day in, day out, sorry. a lot of things have. We also saw some interesting things like athletes training now. It used to be something reserved for very high-end athletes who would wear bodysuits with sensors so that we can know where they were and kind of digitize their movement. So they had to go in a big room with lots of sensors so that we could digitize their racket, their tennis moves or their golf moves and help them improve. Well, now with 2 cameras, you have the same results, and it works really well. So it generalizes a lot. Autonomous driving, of course, you guys know about that. You do some of that. But basically, from 2012 to 2016, what we got out of deep learning and computer vision went up like crazy, right? Massive improvement, massive new applications, lots of excitement, lots of promises. We're building now chips that implement neural networks. We're paying engineers massive amounts of money in machine learning and AI. There's a lot of excitement and good things going on. But there's still some things that deep learning and the current neural networks cannot do, right? I just put 2 examples there, very simple ones. CAPTCHA, right? CAPTCHA should work. CAPTCHA is something that sounds pretty simple, right? Just recognizing letters. Well, these ones are a little hard, but CAPTCHA is one of the obvious examples that is not working for deep learning. You need a lot of images to train a neural net to break the CAPTCHA automatically. Breaking CAPTCHA would mean submitting that image to a system, and the system would automatically transcribe it, right? So you could automatically go to a website that asks you for a CAPTCHA, right? CAPTCHA is still one of the only ways to really know if it's a human behind the computer or not. So deep learning fails at breaking CAPTCHAs. And then recognizing objects that are made of unusual things, like the typical example of the chair of ice, right? A neural network trained to recognize chairs will recognize chairs that are made of wood, whatever, fabric, classic things. But if it's made of unusual matter, it's probably not going to work. So there are limitations, right? Deep learning stalls on very simple things. One of the things that we discussed this morning, and that's also one of the areas where deep learning has not broken into yet, is location and mapping, right? So robot vision, robot navigation, autonomous car navigation, where it's still mostly, there's a little bit of deep learning in it, but it still is mostly computer vision stacks. So old school designer feature kind of algorithms. So they work great, especially in autonomous cars, because you have a lot of different sensors, right? You have LiDARs, you have radars, you have proximity sensors, you have video. So by combining all that, you end up having something that's kind of reliable, but it's not the reliability that you can get theoretically with neural models. Complex scene analysis in general, right? Our brain, our human visual system is really good at understanding very quickly how a scene is structured, which objects are where and where they're moving and how they interact and what their relationship are. One is behind the other, is under the other, related to the other. Deep learning, mostly fails at that now. And some very simple things too, like background modeling. If you want to understand what the background, what's the foreground, there are some deep learning models that work for that, but they're really convoluted and complicated. But the simple analysis, which your brain does pretty quickly, of knowing what's the moving object and what's the background, that doesn't really work in deep learning. So there are now very vocal researchers and people that started criticizing current deep learning approaches with a reason. I mean, the whole industry is rushing into a model that we know has very strong limitations, right? So, it's kind of their duty to warn the world that, guys, let's be careful before rushing too fast on something. Gary Marcus is one of them. Gary Marcus is a researcher at NYU. By the way, as a side note, typical AI researchers come from 3 different kinds of backgrounds. Some of them are mathematicians, like me. We're signal processors. We write equations and software. Some of them are doctors. They look at how neurons actually work, neurologists basically. We call them computational neurologists. And some of them are in the cognitive science field. They're more like psychiatrists. Gary Marcus is one of these. And usually you actually see the impact of that background on the model that I built. It's pretty interesting. And these people rarely talk to each other, by the way. So Gary Marcus published an article that I encourage you to read on Archive, Critical Appraisal of Deep Learning. It's pretty short, pretty easy to read. And that's about deep learning in general, not only for vision, right? But deep learning has these following serious issues. It's very data hungry. You need a lot of data to train a model. You need a lot more than you should compared to what the brain can do, right? Brain can learn with a new type of object with 2 examples, right? First time you saw a Segway, for example, right? Next day, if I showed you another Segway, you'd know it's the same category, right? For a typical convolutional network, you need tens of thousands of Segways to end up finding the common points, right? It cannot deal with hierarchical or relational concepts, like a Segway is somewhere between a bicycle and a moped, or whatever you call it. But there's some object you can relate it to, right? Well, neural nets can't typically do that. They're struggling with open-ended inference, which means that you train them for a specific task or specific knowledge, but they can't do anything outside of that, right? They're not explainable. That's probably one of the most important ones, right? It's very interesting, right? It's still not clear why that works. It's still not clear. I mean, there are a lot of theories, a lot of ways now, like techniques, I would say, to understand what's happening inside a neural network, but it still is essentially a big black box. And it's not. There's no real complete theory of why a neural network works and how it converges and why it does what it does. We just know it works. It's more engineering than science, actually, which is very interesting, right? It's one of the most important progress in the last 10 years in vision, and we don't know why it works. So, but it's there. And that had some problems, right? Especially in self-driving cars. When there's an accident, when the car didn't detect something, why did that happen, right? When you use deep learning to select, or to define the price point of your insurance, how do you know that there's not going to be like biases, in that decision? It's a real issue, actually. It cannot really integrate prior knowledge. So, for example, the laws of physics, right? We have in our brain, we have a sort of intuitive knowledge of the laws of physics, right? Do we really learn it just when we were born, or are we born with it? It's not clear. But there is a preconceived, pre-existing machine for that. There's also a pre-existing language machine in our brain when we're born. And it's very hard to inject that kind of prior knowledge into a neural network. So, and that can be an issue too, right? You can't help the network solve problems more easily because you can't tell him valuable information about that problem. The other thing that may be a little less important, the last one is kind of important, right? It's hard to engineer. You need a lot of data, you need a lot of training data, you need a lot of compute power. You don't really know, you can't really explain why it works or doesn't work. If there's a bug, right, in the software, you're going to fix the bug, write a unit test to fix the bug, and then the bug's never going to come back. With a neural net, you can't do that, right? If one day your neural net mixes up a cat for a dog, well, you're going to retrain it, but you can't guarantee that it's not going to do the same thing in slightly different occasions, right? There's also easy ways to fool it, which is something that are easy to work around. But you've all seen these examples of one face that is recognized as a face, and then you add some high frequency signal on top of that, and that completely confuses the neural net, and then the neural net says this is a polar bear, right? So there's that hallucination problem with neural networks that makes it overall hard to engineer, right? So read that article if you're interested in that in the topic. It's very interesting. So basically, in 2017, Gary Marcus was not the only one, right? There's a bunch of other people who started writing stuff about the limitations of deep learning. And 2017, 2018, when it comes to pure vision neural networks, they started stalling, right? The main conference, NIPS, last year was mostly about reinforcement learning, but not around convolutional networks anymore. We start to understand that we reach a plateau, right? There are some startups that got funded around deep learning, and they have the technology that works, but applications are not clear. There's a lot of companies that have technology in search of an application now in that field. So, you know, it's kind of stalling, but a little down also, right? So we think we're up there because the inflection point was very brutal and went up very, very quickly. But we're actually not there. We're actually stalling right now on the deep learning and computer vision side. So what next, right? There's going to be something next, right? So just so you know, right? I spend a lot of time with the academic community. Everybody's looking for what's next, right? Some people are pushing harder on the current convolutional networks, like Yann Lequin, one of the inventors, is pushing harder and making progress, some kind of progress. Some people are having radically different approaches, getting back to other probabilistic models, other neural models that are more neuromorphic, more like the brain works. But a lot of work right now in the academic community is happening. It's not completely visible yet in terms of engineering, but it's going to come soon, right? So I think that what's going to unlock all that is this, right? Making moving machines see like humans, right? Most of the problems we saw about deep learning for vision occur when you put cameras on top of a moving machine that has to interact with the world and with people. It could be an autonomous car. It could be a robot like the ones you have on the parking lot. It could be a drone. It could be these little Kiwi delivery trucks that are going to bring you your lunch at your desk. But this is the area where we're going to solve that problem, right? Because this is where there's a lot of demand, a lot of expectations. This is also where most of the issues we have are concentrated. So, by the way, in that talk, I'm not going to tell you what's going to be the next big, model that's going to work. I'm just going to give you some hints and my point is just to give you some ideas of where to look and to what people are trying to do to solve it, but not necessarily to tell you this is what's going to work, right? But I think it's going to be in that field. So let's get back to robots, right? Robots have been there for a long time. They work really well in constrained environments, right? In an Amazon warehouse or in a factory, they work really well, right? When it comes to more open environments, usually it's a little more complicated, right? This is Boston Dynamics. It's not a cheap robot company, right? So, okay, I think I'll keep cleaning up my room myself for a little while. So this is, by the way, this is why that problem of grasping and moving things around is exactly why Amazon still hires a lot of people in their warehouses, a lot of them every summer. Not in great conditions, by the way, but this is the only thing that they do. They take one thing, move it to another box, a couple of yards away. That's what they do. That's what you can't do with robots yet. So drones are great. They work great outdoors. But there's no indoor application for drones yet, even though it could be, right? It works. But there's a little bit of issue in navigation, actually. It's actually, I talked to a lot of drone companies, and they don't fly them indoors because it's dangerous, because they would fly into people. They would bump into walls and fall on people. So there's a little issue there. Driving, so you guys know that well, right? And we talked about that this morning. Driving assistance, level 2, 3, 4. Works great. Sorry, it's not a Samsung example. I found it online. Not as good as the one that you guys have, but this is a Tesla example, okay. But full autonomy still has issues, right? So if you look at that, visual navigation is at the heart of all of this, right? If you look at it, right, cameras should be sufficient, right? We load these devices with lots of sensors because algorithms don't work well enough, but we navigate in the world with just 2 sensors, 2 eyes, 2 cameras, right? So cameras should be enough to guide all these devices. And navigation should be human-like, right? We can recognize cats and dogs and stuff in photos super well now. Well, the next challenge is to navigate just like humans do when you're an object like that. So cars, robots, drones should also be able to navigate well when there's a lot of complex things moving around them, right? Which is not always the case today. So this is where I think it's going to happen, and I'm going to give you some ideas that might be a little too technical now, but I'm still going to go quickly over these ideas of new algorithms that are coming out, new approaches that are coming out in machine learning. And this is just a sample, right? There's a lot more if you look around. Probably, maybe the one that's going to win is not there, right? When neural networks started working in 2012, nobody thought it would ever work, right? I programmed neural networks when I was in grad school. It was a joke. It was just funny because it was like a brain, but we all knew it would never work, right? So yeah, I wanted to focus on some of these because they are interesting for specific reason. One thing that's interesting, let's get to the next one. The recurring cortical networks. Okay, this is all technical, but one of the main features of neural nets today is that they only have one direction of inference. You put a signal at the entrance, and it's all going to feed a big network, and you'll look at the output, right? The way the brain works is all different. There's two things missing there. It's the backwards connection. Like when you recognize something, it actually impacts the rest of the network, right? That doesn't happen in classic convolutional network today. And also, it's also missing lateral connection between neurons, right? Which enables the representation of hierarchical structures like that letter A there that ends up being represented by a laterally connected network of neurons as opposed to a single dimension network of neurons in the classic CNN world. So by the way, I put the references of these articles for whoever's interested in getting deeper. So RTNs are promising. I mean, there's no real implementation today. There's other families that are similar. I just picked this one because it's a pretty recent one that's actually a pretty simpler representation of that whole model of lateral and backward connection. It also separates, that's something very important in vision, right? Our brain and our human visual system separates shape from areas, from the texture, right? So your brain computes borders and computes what's between the borders, the area, the surfaces in different ways, right? So these networks naturally encode that, like they're designed for that. That helps these networks, for example, recognize a chair of ice, right? Because the surface is different, but the borders will look like the border of a chair, right? Hope nobody's falling asleep right now. Okay, and I might skip this one. This is you've probably seen these examples where neural networks are basically trained to recognize images as a whole or groups of things. They're not specifically trained for compositionality, like recognizing that. So the output of, if you submit one object to a network and then another one, and then the two at the same time, compositionality would say that the output of object A plus the output of object B should be equal to the output of object A plus B, right? Which is not always the case in neural networks. So there's a way to train networks by enforcing that. But I'm not going to spend too much time on that. Semantic navigation. This is an interesting one, I think. It also is fairly old because people have tried to do that for a long time. But there's been recent progress in semantic navigation that is interesting. So let me get back to how navigation is done today, right? This little robot, as you see out there, has a LiDAR, maybe, or a camera, or a couple of cameras, and constantly digitizes the whole environment, right? It's going to build a 3D model of what's around it using a depth sensor, and it's going to match it to what it knows about the environment, and then extend that model. So it actually localizes itself, so it sees what's around it, and it also knows what the model is. So by matching what it sees with the expected model, it can know where it is, basically. When it does that, it also updates the model of the 3D model of its surroundings, right? So it's called synchronous localization and mapping. So you localize and map at the same time. So these systems are designed to very accurately localize the sensor in a very accurately digitized environment, right? So you can really localize at the centimeter, right, accuracy. That's not the way your brain works, right? When you localize yourself in a room, the way your neurons are structured is that there's a little grid in your brain that can be 16 or 20 or maybe 30 neurons by 30, and you localize yourself on a sort of grid. So it's kind of, if you're in the front or back or left or right of a room, you don't know exactly where you are. I don't know if I'm 5 meters and 25 centimeters from that wall and 15 meters from that wall. I don't know, I have no clue, right? And I don't need to, right, to navigate. So semantic and landmark-based navigation is more based on that. It's based on recognizing landmarks like doors, hallway, escalators, and then representing the environment with a graph, right? There's that door next to that door. Behind that door, there's a hallway, and then there's another door or a tree, or it's really based on landmarks. And then navigation, so localization is based on that. I'm here, I must be there because I see these different landmarks. And then to get to that other point, I need to take that door, make a left, go up the stairs, go at the end of the doorway, the hallway, make a left at the end, and take the third door on the right, right? This is exactly how the human brain works, right? If I give you instructions on how to get to Luke's office, I'm gonna work like that. I'm not gonna give you like the precise coordinates of all the points you have to be in to get to Luke's office. So this is promising. It's not new, but it's coming back, basically. It combines well with classic SLAM algorithms, but it's also much more robust, basically. So, and I think that's it in terms of highlight. Let me see if I forgot anything there. Bayesian networks are very interesting too. So Bayesian inference makes it possible to add some prior knowledge about a phenomenon into an equation, basically. So Bayesian networks make it possible to add some prior knowledge about a phenomena into the network. So that's super interesting. It's for applications like medical applications where you have a lot of prior knowledge when you want to define decide on the best treatment for a disease, or just know what the disease is based on the information you get. It's super useful. Capsule networks, that's the latest attempt by Jeff Hinton, who's one of the inventors of deep learning, to account for the fact that everything is spatially blurred in a neural network. So just giving you some hints. See if you're interested in reading more. But yeah, these are some interesting keywords to dig deeper. So now this is for the theory, right? In terms of implementation, there's also something very interesting that's happening today is that we're making a lot of progress on transfer learning and skill set sharing between tasks, basically. So basically, if you have the different levels, right? If you have a robot that navigates, let's say on the Samsung campus, right? And then another company, so let's say it's that Nightscope robots, right? Tomorrow, Samsung hires a cleaning company that's going to hire robots. Well, these robots are going to share the same map of the campus. So there's definitely a big interest in sharing that data somewhere, right? So navigation occurs on the edge, but data sharing occurs somewhere on the cloud, and data update occurs in the cloud. So you have a loop there between the edge and the cloud. Now to go a little further, when you train robots to do things, you use reinforcement learning. When you use reinforcement learning, you can actually very easily share some parts of the network across tasks, right? You can teach a robot to clean the floor and another robot to roam around the campus to look for problems or for potential intruders, and there's some parts of the network that you can share. So the more robots you have sharing experience on the same cloud, the better you get, right? So there's real sense in having that distributed cloud versus edge, and feedback loop between the two in the next, successful implementation of what we're talking about here. That's pretty interesting, right? The fact that that a totally different experience can be leveraged to improve the performance of a robot in a different environment for different tasks. It's pretty exciting. All right, so, and visual navigation, if a successful visual navigation for moving object like that works, it's going to unlock a lot of potential markets, right? So cars, first of all, right? Cheaper, more robust, more reliable, autonomous vehicles, delivery robots, right? Today they can't have like tons of LiDARs on them because it's too expensive. If they can work with, let's say, 8 cameras, then you win. Indoor autonomous drones for building inspection, real estate, inventory, security. This will all make a lot of sense. Helper bots, it's not there yet, but it's starting. You start to have robots in hotels. A company called Savio is actually distributing robots to carry things around in hospitals and hotels. Cleaning, security, like the ones you have outside, marketing robots, etc. So, just to finish, I think it's a perfect storm is brewing. Neural algorithms are emerging. There's a strong need, strong and high expectations on some features that are not completely there yet. And there starts to be some frustration with legacy technology. So if you're at the intersection of edge computing, AI, and cloud, if you can set that up, and of course, if you can hire the right computer vision and machine learning engineers, which is very scarce today, I think you can build the next edge/cloud AI platform for moving machines in the next 2-3 years. And there's going to be 1, 2, maybe 3 winners in the game coming up. And that's it.
I guess we can have some questions. I'm going to start with one, so because I have mics to take advantage of it. About explainability. So I was in a meeting with Yann Lequin a week ago, and he was telling me that he can actually explain everything, and this is not that of a black box. And that the only reason we say that we cannot explain is because we are lazy. What do you think about that?
Say it again, the last part? What's the last part? I didn't get it. The last part of what you said?
He said that we are lazy. This is our laziness is the reason for which we don't explain.
Yeah. I mean, this is it's a major issue. I mean, I would say that there's ways, though. I mean, it's a little exaggerated in the sense that there's ways now to understand what's happening. By basically rerouting the way a neural network works, you can do you can create images or create sound or create stuff from the network that can explain how things work. I mean, what can I say? It's one of the massive issues,
Questions?
Thanks, great talk. I'm curious what what's a lot of the news right now is about these AIs getting biased by the programmers that are creating them. So what are your thoughts on how we're going to get the diversity that us humans have as a society, that these AI algorithms are going to have that same diversity?
Yeah, that's a great question. I was chatting with somebody at Facebook recently who runs AI over there, and they have that issue in the sense that all the engineers who build AI systems, they're pretty much male, unfortunately. It's changing slowly, and that actually had some indirect impact on the algorithm. It's also about the data you use, right? And the problem we have with deep learning today is it depends so much on vast amounts of data, and it's hard to add prior, instructions or knowledge to the network to tell them, okay, this is the training set, but don't discriminate based on this or that. It's impossible, right? You have to do it after the fact, and it's hard to implement. So I would say that we'll find ways to make it happen. We'll find ways to have more balanced data sets. There's a lot of questions and a lot of work on that today. I can't tell you how it's going to work. Honestly, I don't know. With the current models, it's just impossible. So, yeah.
Hi, thank you. You talked a lot about the models, the algorithms that need to be developed or improved. What about the sensors? You mentioned a couple times, like we have 2 eyes and we can drive, and a car needs 20 eyes and a LiDAR. So what are the sensors that are missing or should be better, should be different?
Yeah, great question. We were talking about that over lunch. There's, one of the issues with video today is that you sample every 25 frames per second, every 40 milliseconds. You take a sample of what the sensor sees, and this is not at all the way the brain works, right? The brain works with impulsions. When something so when your brain looks at, when your eyes look at a scene, whenever something changes, the brain receives a signal that's +1 or -1, right? So that spikes. It's called spiking neurons. And I think that one day we'll make a lot of progress in AI when we can actually implement spiking neural nets, because they potentially solve many issues around movement, the understanding of movement, the understanding of complex scenes. But I think we're all far from that, and one of the limitations is that we don't have the sensors for that. So there are sensors that work like that. I think you guys at Samsung have one. There's other companies that make these sensors that have very accurate temporal precision and work in shots like that. So +1, -1, every time something changes, with a super accurate temporal precision. That would be a very exciting sensor that could potentially change a lot. Yeah, cheap LiDAR, of course. LiDAR is super useful, even though you get a little further from the human brain there, because we don't have a LiDAR built in, but it's coming. I mean, the LiDARs now that could be in the couple of $100 that will generalize. I would say these are the two directions. I'm not a huge fan of never-ending high resolution, because at some point it's good to have a focal that can move, but processing more and more pixels just costs more money, right? And it's not necessarily to the benefit of the eventual analysis you have of your scene. So I don't think we need a lot more resolution. But yeah, we need these two sensors.
Thanks for the presentation. So we now know AI now is becoming more powerful each day, and the AI engine can do a lot of things. But do you think AI engine do you think the machine can really understand what it sees and what it's listening to? And if the answer is no, do you think it can understand in the future? Do you think that the machine can really understand what it's seeing, what it's listening to? If the answer is no, when do you think we can achieve that? Thanks.
One of these models, yeah. Today, I mean, you can model a scene using traditional computer vision approaches, right? I mean, with my last company with Placemeter, we had no deep learning. We had classification to recognize cars from pedestrians, from bicycles, from motorcycles, from trucks. We have 5 categories, which was pretty simple. So we used the AdaBoost kind of model to classify that. Works great. And then all the rest was computer vision. So we had a complete analysis of the scene. We detected every object. So we had background modeling, object detection, tracking. So at any point in time, we had the identity of each object in the scene. Well, 85% accuracy, and then a track of where it came from and a prediction of where it was going, right? So with traditional models, you have that. But squeezing that into a neural model is super complicated. I mean, even in these models, it's not completely clear and obvious what's going to be the final model that works. I would say compositional models like the RCN, the recurrent cortical network, would be probably the right direction. Not going to be exactly that, but something in that field where you have these lateral connections and the feedback connections too. But yeah, that's the big challenge. that's a big, the next frontier.